Yeah. So that next topic then of trying to make neural networks work better, where I had doing effective deep neural network learning is what I had, is basically to say, how do we overcome problems like this? Yeah, yeah. Trying to find time to read all these things and keep up with them is a challenge for everyone. That's part of why I'm doing it this way today with these things. I was looking at the slides I had already, which like, actually, these are not sufficient anymore. But the time to update them and keep up with it, it's hard. You guys are going to focus on, because you're learning it on the course, focus on the tasks that, you need essentially for the assignments, and your own learning here, but hopefully it's also providing a basis for your continued kind of reading and exploration of this. So we're really going to try and make the last assignment be a bit more open and free, that we're giving these problems saying basically use a fully connected or a CNN approach on these two data sets and try something, right? So we're going to evaluate that you kind of described your model, whatever it was, you've analyzed it, whatever it was, and how well it worked. But beyond that, if you want to try something different and explore other models that are more interesting to you, you can do that, right? Because the two data sets have a bit of a structure there. So the COVID data set in particular, you could just do fully connected like we're talking about. You could talk about some of these regularization methods that we're about to talk about, or you could try to focus on the time aspect, right? Don't worry about all this, the fancy methods I'm going to talk about here, but you could talk about time, because in the COVID one you have people being infected and lead time from test to second test or whatever. You could try to learn patterns over time, but we want to basically give you a chance because there's too much to cover all in one course anyways. So it really helps if you focus on an area you're interested in, especially grad students. Hopefully you're focusing on research, or at least pretty complex jobs. You need to be able to have your own set of interests in this area and explore it. So what problems do have neural networks? Neural networks are great. Why could they have any problems? One problem they have is overfitting, as I've mentioned a few times. Another problem they have is as I showed a bit with those weights, is that they're not very efficient for certain types of outputs. So this fully connected feed-forward approach that we're talking about right now, think about what it would be good for, right? So for the COVID data set we talked about, seems sensible. You have a bunch of numbers, a bunch of labels that you turn into some kind of number. You have an output and you try to do a prediction on them, right? But we don't know any structure amongst that data, right? So there's nothing we can do. So we just take all the inputs, fully connect them, have lots of weights, and we have all the outputs, and we try to learn them. But if your data has interesting particular properties, like images, like we were showing, pixels have a spatial relationship to each other, so it's relevant where they are and how close they are to each other. Time series data has a very particular structure, right? So some of your values of your variables relate to ones from the previous time steps, or might be from very distant time steps in the past. That's not captured by what we're talking about so far, right? And also the way we're doing it now, if there's a very large number of outputs, they'd be pretty problematic, because you're kind of assuming you get this efficiency that at the end you have a few labels you're training. If you have thousands of labels, it's very hard to train them with what we've talked about so far. So they can be slow to train. Another problem they have is overfitting. That I think has come up before. There's some other particular problems like vanishing gradients and catastrophic forgetting, which we're just going to briefly mention because I didn't have details typed in for some reason, but we'll try to get the intuition of those. And interpretability is something that people often critique with these, and we don't have a solution for that, but we can talk about ways to try to interpret them as we go forward, because we're essentially building a black box with lots of parameters that don't mean anything, right? even if we have a nice model that has a bunch of layers going forward into each part of the future, we don't have any interpretation for what these mean, right? They're just free parameters trying to get us the right output. Maybe in this kind of convolutional thing, we can start seeing that there can be some patterns because the relationships between the nodes are about the previous layer only. But it's actually very hard to get an interpretation out of them. Okay, so basic heuristics for improving this backpropagation. Like we said, backpropagation is still the thing that everyone uses, and actually people want to improve it. But what would work? So why would backpropagation be expensive or problematic? Like, it's basically doing a lot of computations and gradients on all these parallel nodes and variables. So if we have less hidden nodes, right, it's gonna help make it run faster, right? The more hidden nodes, the more hidden layers you have, the more complex it's going to be. But if you remove them, your model's going to be less rich, right? We just said deep is good because more hidden layers are helpful. So how do you remove nodes without removing that benefit of the deep neural network? There's a couple approaches to try to do that. You could try to overcome some of the stuff by training multiple networks and varying the sizes, right? So saying, try them out, right? So try different numbers of hidden layers, different widths, like how many hidden nodes there are in each layer, and try to pick the best one. But then that's even more expensive to train because you got to train all of them. But you can optimize your design by searching. So there's people actually at Waterloo who do that very explicitly in system design. They kind of do an iterative approach where they kind of learn a really good model that's large, and then they iteratively try to basically knock different parts out of it to see if it damages it or not, and then they pick the ones that work better. Because the more nodes and layers you can remove, the faster it's going to run, right? Obviously, we're going to do our validation training test approach to try to optimize the performance. And I guess I don't have this on the slide here, any of the slides here, but one thing you can do here then is that, well, okay, it comes up in the next thing. Right, because we got the, I have a better picture on this later, but number of weight updates. So there's a number of updates that you've been doing as you've been training it. How many times you ran kind of backprop over and over. And here's your error. The darker line is the training error, and the hashed line here is the validation error. And so you hope you're going to see this, right? This is what you want. You're basically going to go down as you training. So there, is that good? No, you don't want that. These are both examples of things that you want to watch for, right? You do expect that your training error is going to get better. You would hope, right? As you train more, the data on the performance on your training set, if you compute the error and report your error on your training set, it's interesting just to see how it's working, but it doesn't really give you the unbiased result of how your model's doing, but it helps you tell where you are right now, right? You can't use it for evaluation, but you can use it while you're training to decide what to do, essentially. So your training error should go down, but your validation error might have this problem where its benchmark goes down for a while and then it starts going up, right? Here we had even more explicit one where it might go down and up and down. And this could be, right, because it reaches some point that's kind of maximum, and it gets really good, and then you start doing more and more and you start overfitting, right? So this gap here gives you how much overfitting you're essentially doing, because you're now doing worse, right? On the test data, because you still never see this validation data that you're seeing, right? In this case, it doesn't improve at all. Here you got lucky and it kind of kept improving for a while. But in essence, you're usually going to be expecting this is going to start going up again. And what you want to do is pick some point, there's not an n, that's just a point, to stop, right? And so I don't think I have it on the slides here, but early stopping is another simple type of regularization approach where you just say, let's watch a graph like this, and once we get to the point where we're sure it's really improving again and I'm getting worse again, that the error is going back up on the validation set, we go back and we pick the best spot and we stop. And that's the one we freeze and we run on the test data, right? And we get this one, and then you run it on your test data. So that's this this early stopping approach that I should have actually in here as a way to use this. And it seems like cheating. It's not cheating as long as you're doing it on your validation set to decide on the early stopping, and then you compute your results in the test set. But it's something you have to kind of do sometimes because you don't know whether you've gone too far in terms of training. And then dropout is another one that kind of uses some of these ideas that we've talked about. Oh, we've talked about activation links already, so try them out, right? That's why I said yesterday. Which ones work better for your domain? As we've said, most people's advice is to start with ReLU, but other ones can be effective sometimes for particular data sets, and no one knows why. It's an interesting area of research. Okay, I'll do that one in a minute. I was talking about this fully connected versus not fully connected, and so the simplest kind of regularization method that takes advantage of that to understand it was this one, and that was one of the main things that Jeff Hinton at U of T kind of helped introduce. But a bunch of these basically tricks that we're talking about here were the things that made together neural networks kind of work more effectively, because if you don't deal with these problems, they just overfit or the gradients kind of go off to infinity. So we said we want to have less weights, right? That'll make it faster to run at test time. It'll make the training more robust because it's not overfitting all the time. We talked about a particular way to remove weights for images, right, which is very focused on the structure of an image. But how would you do that in just general data? Like if it's not an image, you don't know anything about the structure, you can do it randomly, right? So this seems like a really bad idea that works. And when they were talking about doing this, like, we just knock out weights, we try, and everyone's like, but why? Why does it work? Like, what's the model? Like, what's the formula for this thing? It's like, I don't care. Jeff and Jim would just talk about that. We're like, oh, it doesn't matter. It works. We try it. And then we'll figure out later why, right? So what you do is while you're training it, you randomly turn off some of the units, right? So you just pick a bunch and you say, I'm going to knock these out, and you literally get rid of that arc, right? Because every one of these used to have a line between them, right? Every node, they're all missing, right? So you just knock them out, and then you train that update with these ones knocked out, and then the next round you come around, you randomly pick a different set, and then you train with those, right? So that means that every node now isn't getting to see all the data, right? So you have a test set that you're training the network on all your test data, and a validation set that you might be using for early stopping, but every individual node doesn't necessarily see all the training data, right? It'll see certain ones sometimes and certain ones other times, and maybe one time that it sees the data point and it's been relying on this node to give it the right signal on its function, the next time it gets trained, that guy's not there, right? And so it has to adapt to that. So it forces all the nodes to basically learn more robust functions. And it also forces them to diversify. So this one might focus on some certain patterns that it can capture, while other nodes focus on a different pattern. Because they're all working on this together, right? We've got a global loss function that we're trying to optimize over the entire network. And we're really trying to do that for all the weights. And since they're all trying to work together, these weights, as we're updating them, but when you force them basically not to be able to rely on the nodes around them, they can't overfit to any particular nodes. Sorry, not the nodes around them. They're all connected to all nodes from the previous layer. But since the inputs and outputs might change, they have to learn a lot of that function themselves. And again, it's not fully understood why this works. It's just that it helps increase robustness because you're reducing the number of weights, and they all have to basically do that. We had this idea of overfitting. I think I talked about this a bit when we were talking about those SVMs, just what we're trying to get at, right? Assuming there's a right answer in here. Right. Well, it depends. Oh, this one you're still getting some of them wrong. So there's red dots and there's green dots. It's a very hard figure to see, sorry. So underfitting, you know, you would be saying you're basically not good enough because you're not really dividing these points that well. And I guess in this figure they're saying this is the good one, and this is like under fitting, and this is overfitting. It's debatable whether this is really bad or not because it's doing pretty well getting a lot of the points, but the shape's kind of off. But how far do you go to capture just that one node, that one data point, if you're doing all right at the other ones? But a lot of times people would actually want a model like this that gets you some of these data points. Unless you think these are noise, right? If these are all noise, maybe you shouldn't be capturing them. So it's not its best figure. But the idea with overfitting, though, right, is that you're getting a model that's super particular about every data point. So you want to avoid that. So dropouts, one way of doing that. We talked about that. We talked about that. Talked about training. These are just kind of general. There's no real method for that. Learning rate over time. Okay, that'll be good. Why don't I have... Because there's standard regularization. So the thing we were talking about, we were showing before from the paper, from the textbook, was this idea. So we're going to add weights to the neural network. Sorry, to all weights in the neural network, we're going to add an additional kind of cost. And this function can be anything that basically combines some or all of the weights and adds a cost function. And then when you're trying to minimize, this is going to be something that takes into account, right? So the two most standard ones would be L1 and L2 regularization. And L2 is just that L2, like summing and squaring the components, right? These are all vectors, so it's really our, what did we have it called? Our distance function, where you've just got that order, right? So it's really just the sum of the weights, and if it's a 1, it's L1, right? Which basically just means it's the absolute value of them, right? So it's always absolute value. But when you square them, then you get the absolute value for free. So that's our L1, that's our L2, the weight squared. But it's a distance function, right? So we had it before where, yeah, sorry, it's the difference between the true label and the predicted label. But they'll basically have two different effects on it. So if you're just doing this kind of sum of the weights in general, the absolute value of them, you can be saying any weight here that has any value is going to be bad. So the more that closer to 0, the better you'll be off. This one, L2, would also like them to be 0, but it's more important for it to get the ones that are down. Since you're squaring it, any values that are kind of much higher than the others are going to get minimized. So it would encourage the weights to be more similar, right? So like reducing peakiness, but you could also just say encourages weights being more similar to each other. if that makes sense. You can read it. Okay, so that's another method. Sorry. That's there. Are there any questions about stuff so far here? About why we're doing it, or what how these work? Let me see if they have any stuff here. Yeah, so in the slides from that textbook, again, they have a chapter 7 on this. Is in that book is on essentially these methods. They just call that regularization, the chapter. And that's kind of this idea that regularization is any method that reduces overfitting is a regularization. So sometimes people just explicitly mean L1 and L2 regularization as that. They think that's regularization, but anything that reduces overfitting is a regularization method. So you add weights, you randomly drop arcs, something like that. Those are all regularization methods. It's just more of a methodology. So there's a bit more description on what those two do. And then I guess there's ways of thinking this as moving in the optimization space of those weights. That if you're adding these penalty scores, you're basically adding another target that is trying to optimize, right? Because you're trying to optimize the original target, which is, I assume their W star is the original loss function. So you're trying to go down this curve, but then you're also adding some other constraints saying you shouldn't be too far from 0, and maybe you could add other functions, right? So you could consider these ones as essentially creating another target in the optimization space, and now you're trying to optimize both of them. You're doing this iteratively through gradient descent, but it's going to basically try to satisfy both. And so the perfect solution will be something that is, intersecting on both systems at the point that maximizes everything. So that helps you kind of think of it that way.